Hi, so welcome back to the lecture series on points at topology. In the last session, we have discussed regarding something called limit point, interior point, and I gave you some time to brush up all the topics that we have discussed in a couple of videos in the previous times. So, because from now onwards, we are going to rigorously use those concepts, okay? So, we are starting something called today continuity. Okay, so before studying continuity, let me just briefly recall that what you have seen the continuity in real analysis course, that what is continuous function in real analysis. So suppose we said that suppose f is a mapping from R to R, so this is said to be a continuous function if for any epsilon belongs to real number, comma epsilon larger than 0, there exists delta belongs to real number, comma delta larger than 0, such that when mod of x minus x naught is less than delta, that will imply mod of fx minus f of x naught is less than epsilon. So that means whenever I have, so let's say here is my x naught, and let us consider this is my curve. Okay, so here is my f of x naught. So the continuous at the point x fx at the point x naught implies that suppose we consider a neighborhood, whatever with the width of the neighborhood, let's say it is maybe a very small neighborhood, let's say epsilon neighborhood like this. If it is my neighborhood, then of course I should get certain neighborhood around x naught as well, that is around x naught, which is basically of delta neighborhood. So you see that here the neighborhood is of the form fx f of x naught plus epsilon, and this is f of x naught minus epsilon, and here it is delta, so x naught minus delta to x naught plus delta. So I should get certain neighborhood delta neighborhood around x naught, such that whenever I take any point from here, this should map inside this particular neighborhood, I mean inside this particular epsilon neighborhood. It should not go to beyond anywhere, something like that. So that is the continuous function definition. For example, if we would have certain discontinuity here, okay, so then there is a open open channel for this particular point. So it may be defined from here as well. We couldn't do anything, right? It could map certain point here, let's say it is my f of y. Okay, so that's why the continuous function means it must be there should be, if we have any neighborhood around f of x naught, we must get certain neighborhood in x in the domain as well, so that the entire domain in the neighborhood is mapping in the neighborhood that we have chosen in the codomain. All right, so now let us try to generalize this concept. First we just generalize this in normal arbitrary metric space, then we'll try to generalize this in arbitrary topological space. So you see one thing, that let us verify this one. So it's saying that whatever epsilon I choose, this one, so it says that whatever epsilon I choose from this, I should get certain delta. So that means such that this domain, so okay, what does this basically means? This is basically the open interval x naught minus delta to x naught plus delta. So whatever element I will choose from here, this should exactly map to f of x naught minus epsilon to f of x naught plus epsilon. So that means basically this is equivalent to say that f of x naught minus delta comma x naught plus delta is subset of f of x naught minus epsilon to f of x naught plus epsilon. You see that there are arbitrarily many points in between these two. In this particular neighborhood, there are so many points, but those may not be in the those may not be any image or of any particular point in the domain set, right? Because it may not be surjective as well. So that means it is equivalent to say that f inverse of f of x naught minus epsilon comma f of x naught plus epsilon, this one is basically x naught minus delta to x naught plus delta. So just give this as condition star because this is going to be helpful. Now suppose we have an arbitrary metric space. So first derivation in metric space. Let us consider that x comma d is a metric space. Let's say d1 metric space and y comma d2 be in another metric space. Alright, so if it is both are metric spaces, let us consider f is a mapping from x comma d1 to y comma d2. So then this function is said to be continuous at some point x naught belongs to capital X, such that if for any epsilon belongs to real number, epsilon larger than 0, there exists delta belongs to real number, delta larger than 0, such that whenever for some, let's say whenever for any x belongs to capital X, mod of x, not mod, this is d of x minus x naught is less than delta, this will imply d1 and d2 of fx minus f of x naught is less than epsilon. So you see that basically I am taking an open ball of radius delta at with radius delta set and centered at small x naught, and here it is b epsilon f of x naught. So that means it is a open ball around f of x naught such that this is equal to f inverse of this. Okay, this is a definition of continuous function at a certain point x naught. But if it is suppose f from x comma d1 to y comma d2, this is continuous at each x belongs to capital X, then f is said to be continuous. Alright, continuous at x itself, at the entire x itself. Okay, now what about in case of topological space? So now in topological space we don't have the luxury to choose such a beautiful open sets, right? Rather we have the luxury to choose any open neighborhood, whatever be the neighborhood. So that means, for example, suppose, so now in derivation in topological spaces. So suppose f is a mapping from x comma tau 1 to y comma tau 2, so it is a function is said to be continuous if there is a continuous at x naught if for any open neighborhood u fx naught around f of x naught we have vx naught. This is open neighborhood around x naught in x such that f inverse u of fx naught equal to vx naught. So that means whenever I choose any open set around fx naught, the inverse of that open set has to be open in x. Okay, so basically this particular criteria, this is the key property to generalize the concept. All right, now there is a, so then we say that is continuous at particular point x naught. So of course that suppose f is continuous at each x, then f is at whole x. So now there is a lemma that says that suppose f is a mapping from x to y is continuous if and only if for any open set v of y we have f inverse v is open in x. So if part is very trivial, that suppose f is a mapping from x to y, so let v is subset of y is continuous. Subset of this is open set, then I consider small y belongs to capital V, such that f inverse small y is not empty. So if f inverse small v is empty, then we are done, we have nothing to prove. But if f inverse small v capital V is not unit, then we could have something that suppose f inverse y is not v. So then let's say small f of x equal to y, then as it is continuous at every, then of course f is continuous at small x itself, so I choose u f x to be as v itself, then f inverse u f x is open, course, I mean, there exists some neighborhood, let's say okay, we have chosen ux, right? Okay, let us take it as vx. Just consider v as the open neighborhood around v, around fx. So then we choose there exists ux is subset of x, this is open, and ux is subset of f inverse v of fx. So then f inverse v fx equal to union of all x such that y equal to fx. So alright, you can say that it is union of all v of y. F inverse v is basically f inverse v is equal to v of x, where x such that f inverse so that fx equal to y. Okay, and comma y belongs to the natural number, comma y belongs to v. Okay, so then this is open set. So f inverse v is open set, and the only if part it is very trivial, that suppose we have v, this contains at some small f of x naught, then f inverse v, this contains x naught, so it is open, and it is true for all x naught, and it is true for all x naught belongs to capital X. So f is continuous at x naught. Okay, so you see that suppose we have two topological spaces. Let's say it is my x, this is my y, and I have a map from f from here to here. So suppose we have in open set this, I'm sorry, not here. Suppose an open set here, that is v. So there also should be certain open set here as well that will be completely inside v via this small f. So this should be a channel like this. Okay, so there is a continuous function pictorial representation. So now you see that one thing, that suppose you have a topological space x comma tau. So whatever be your topological space, I can always get some basic open set of that topology. Means I can get certain open set which are very fundamental of that of all the open sets in a topological space. So that is the basis of a topology, right? So the next corollary, this says that suppose f is a function from x to y, then f is continuous if the above lemma is satisfied for each, or let me write the lemma itself, if and only if for each basic open set v, we have f inverse v open in X. So if it is continuous, then it is trivial. So if part is very trivial, there's nothing to prove. But if we consider, let's say, the only if part, so let's say so only if part says that suppose f is a mapping from X to Y, says that whenever I take any basic open set from Y, the inverse of that basic open set in X, this will be open in X. So if we take any open set, let's say V subset of Y, of course it is non-empty, then V could be written as union of all, let's say alpha belongs to this V alpha, where each V alpha basic open set. Okay. So then F inverse V equal to F inverse of union of alpha belongs to index at V alpha. So it's nothing but F inverse of, sorry, is nothing but union of alpha belongs to this index at F inverse V alpha. So each F inverse V alpha is open. So this entire set is open in X. Okay. All right. Now you see one thing, that suppose we say that A is smaller than B. So that basically implies that the injector is injective map from A to B itself. Okay. And it is strictly, but I is not same as the identity one. And also we can, not this way, so such that the codomain of I is larger equal to 1. Yeah, means it is equivalent to say that I is not same the identity map 1. So that's why we can define the smaller or bigger subset in terms of the identity maps. So remember that we have also talked about, suppose we have x comma tau 1 and y comma tau 2, these two are topological spaces. So once we have these topological spaces, we can talk about let's say, okay, not x comma tau, yeah, once there are two topological spaces on a certain non-empty set, then of course we can talk about whether which one is stronger, which one is weaker. So that means, and the weaker and stronger property, this could also be analogously identified in terms of the identity maps. So for example, suppose, so that is a corollary. So the corollary says that suppose we have x comma tau 1, let us name it as x1, and x comma tau 2, let us name it as x2. These two are topological spaces, and let us say that so tau 1 is subset of tau 2, means tau 2 is finer topology, so tau 2 is finer if the identity map which is from x comma tau 2 to x comma tau 1. This is continuous. This is if and only if condition. Suppose, but now let us assume that suppose it is finite. So if we take any open set here, let's say here is any open set V from this subset, so it is open in tau 1, and tau 1 is subset of tau 2, means this V has to be open in tau 2. So then I could check the considered identity inverse of V itself as V. But conversely, suppose identity is continuous map, then whatever map I will choose here, V, so what is identity inverse of capital V? It should be V itself. So this has to be open in tau 1, right? So that means both the statements are basically equivalent to each other. For example, suppose we have R is a set of all real numbers, and most usually we can talk about R with respect to Criterian topology. So here the basis is the form A comma B such that next to R. So it is normal Criterion topology, and also you can talk about something called the lower limit topology. So here the basis is closed A open B such that B. Okay, so then any open set A comma B, so this is open set in this belongs to tau of ED. How can I write it in terms of this? So this can be written as union of all n belongs to natural number A minus 1 by n comma B. Okay, now each are open. Now this is in tau L, so that means tau ED is subset of tau L. So that means the identity map, there is identity from R comma tau L to R comma tau ED. This is continuous. Okay, so let me give you a small exercise, just it is a brainstorming exercise. Find an example where identity from x comma tau 2 to x comma tau 1 is not continuous. So that means you have to find a particular open set, particular non-empty subset capital X, and to topology tau 1 and tau 2 over that such that none of them are finer than another one. Okay, all right. Now there is a lemma. I'm sorry. So suppose if it's a mapping from x to y sub function, then the following conditions are equivalent. So first of all is f is continuous. This is if and only for any closed subset V of y, f inverse V, this is closed in X. And number 3, f of a closure is subset of f of a whole closure. It is for all a subset of X. So first of all is f is continuous, so that means so now first is 1 to 2. So for any closed subset, let's say V subset of y, this is closed, then V complement is subset of y, this has to be open. So f inverse V of complement, this is open in X. So f inverse V of complement means f inverse V whole complement, this is open in X. So that means f inverse V is closed in X. Now how to get from 2 to 3? Suppose A is subset of X. So a closure, so I mean, you see what we need to prove it. So we need to prove it that a closure is subset of f inverse f of a whole closure. So you see that a subset of X, so f of a is subset of f of a whole closure, right? So that means now f inverse of f of a whole closure, this is closed, this is closed set. So a is subset of f inverse f of a whole closure. So that means this is a closed set that contains capital A. So now a closure means, so a closure has to be subset of f inverse f of a whole closure, because if f of a closure is smallest closed subset that contains A. So that will imply that f of a closure is subset of f of a whole closure. And finally the third one, that suppose V is subset of y, this is open. So we consider that Z equals y minus V, this is closed set. Okay. So of course we have Z closure equal to Z. So f of Z is inside f of Z whole closure. Now, okay, not this one. So I mean, okay, you see that so it is closed in Y. So then we can consider that A to be f inverse Z. So if it is f inverse, so f of a closure is subset of f of a whole closure. Okay, so f of a whole closure, this is subset of Z closure, means it is Z. So f of a closure is subset of Z, right? Now F in, that means A closure, this is subset of F inverse set. So F inverse is nothing but, so that means A equal to A closure. So that means A is closed. So that means F inverse of y minus v, this is closed. Now F inverse of y minus v means it is x minus F inverse v. So this is closed means this is closed. So that will imply F inverse v, this is open. So that means these three particular conditions that we have mentioned here, these three are isomorphic to each other. So what is the usefulness of this set? So you remember that at the beginning of the course of topology, we defined that we said that topology may not be defined in terms of open set only. So it may be defined sometime based on closed sets. So once, like Jarsky topology, sometimes the closed sets are very easy to work with. So in that time, this particular condition will be helpful to study continuous function over that kind of topological spaces where closed sets are the fundamental object to be studied. All right. So this is the continuous function criteria. So now in general topology property have defined, but some of you may be interested, may have already thought about that. Once at the beginning we have defined how we define topology in terms of in real number, right? Like here. So there we define the topology. Here you must have thought that maybe sometime in real analysis we define the continuous function in terms of sequence, right? So that means if we have any convergence sequence, then if it is converging to a certain point, then the functional values will also converge at that value of the function at that converging point accordingly. But is there the same analogous thing in general topology? The answer is yes, there is. So that is something called sequence lemma. So what does the sequence lemma says? The sequence lemma says that suppose X be a topological space, that A is subset of X. Let Xn is a sequence in A such that Xn says that Xn is converging at X. Then X must belongs to A closure. Okay, so that means it is very easy. Suppose we have, let's say, we have topological space X, A subset of X. So once we have that Xn is converging at small x, so what does it mean? Whatever neighborhood I choose around small x, this must contain one element Xn belongs to this. Okay, so that means and Xn must not be same as X. So that means X is a limit point of A, because Xn must belong to capital A. So x must belongs to a closure. Okay. Now this implies sequential criteria, that is the sequential criteria that says that suppose f is a function from x to y, this is continuous at x naught belongs to x if for any sequence xn converging at x naught we have f of xn f of x naught. So sorry, there is a, I'm sorry, if f is continuous then it is true. Yeah, so let us consider f is continuous at certain x belongs to capital X. So of course if we consider any open neighborhood, let's say v f of x naught around f of x naught, this must contain certain element, let's say f inverse v x naught equal to some u x naught, let's say v f x naught. Okay, is u x naught. So u x naught must contain x naught. So that means there exists certain xm that is mapping to there. So that means v of f x naught, v of f of x naught, this must contain some f of xm. So that means, and this is true for all m rising to capital, so up to certain capital N is there. That means f of xn is converging at f of x naught. So this is sequential criteria. Now when the converse statements of these two properties are true, we are interested with conversion, right? So conversion may not be true every time. May not be true every time. So when it will be true? It will be true if x has a countable local basis at x naught. X naught means what is where it is to continuously getting to be checked. So this is a small exercise for you. Okay, so you try these two exercises and let us stop it here. Maybe in the next class onwards we will see some more properties of continuous function. Okay, thank you very much. Revisit all these topics and get ready for the next class. Bye.